Everyone is shocked simply due to 99, and to address every inquiry, please watch until the end. After years of doubt, groundbreaking new research has brought LK99 back into the spotlight. We'll be looking at the latest results that suggest LK99, a copper-swapped lead desire, might actually show near room temperature, the hard-to-find Meyer effect, what this find change the way we think about superconductors, so hold on tight as we talk about how LK99 is pushing the limits of modern science and could lead to technology advances we've only dreamed of. So what was LK99 and why were the initial claims so controversial? The original reports that LK99 was at room temperature are at the heart of the dispute. Superconductor. These claims were met with a mix of excitement and doubt in the scientific community because of what they could mean for future study. However, later efforts to repeat the experiment had mixed results, with some researchers claiming similar results. Others were not able to replicate the supposedly superconducting state. A big part of the debate comes from the fact that the first claims about LK99 were made public on a preprint server, where papers haven't been reviewed by other researchers. This led to a lot of people trying to repeat the results. Some of them were even live-streamed on social media sites. However, more evidence has since come in that contradicts the original claims about LK99. Several research groups have put out studies that disagree with the original claims. Some of these studies show that any perceived superconducting properties were probably caused by flaws in the samples that the University of Maryland's Condensed Matter Theory Center, for example, said that LK99 is not a superconductor even at room temperature, and called it a highly resistive, low-quality material. Another study said that an impurity in the first samples of LK99, called coppery sulfide, could explain some of the properties that were seen. Despite these claims, researchers warn against completely dismissing the original claims because impurities and tweaking things like composition or firing time may still reveal superconducting properties. However, experts agree that LK99 is not a superconductor, or at least they did until this new paper came out. The subject of the paper is copper was used instead of lead in the abstract to study the mere effect at room temperature. They talked about what they had seen with LK99, a copper-substituted lead apatite. They discovered that when LK99 is below room temperature, it behaves like a superconductor. For example, in a 25 OA magnetic field, it acts diamagnetically, repelling the magnetic field. At 200 OA, it changes its behavior to paramagnetically, attracting the magnetic field. They also noticed a special memory effect during cooling, which is important because it's where they found histoparis. Loops below 250 K show that the mere effect is present, which is a sign of superconductivity in this material. This section and this part of the paper explain that a material must show the mere effect, which is perfect diamagnetism, in order to be called a superconductor. This has to do with how it acts in magnetic field and temperature tests LK99, a type of copper-replaced lead apatite, is a possible superconductor at room temperature, but this effect hasn't been fully shown in previous studies. This paper describes how modified LK99 samples were made to get rid of unwanted magnetic properties, and the exact steps that were taken in their experiments to see these superconducting properties. Let's read the rest of the paper to see what happened, and then we'll look at what other people have said. What the researchers said about the study. They looked at how a certain material responds to magnetic fields at different temperatures. To do this, they tested the material's magnetism at two different strengths of magnetic fields and moderate, and at temperatures ranging from cold 100 Kelvin to warm 300 Kelvin to warm 100 Kelvin. The material usually moved away from a light magnetic field. The field of magnets, something called diamagnetism. When the magnetic field got a little stronger, the material started to stick to it. This is called paramagnetism. This switch happened around a certain magnetic field strength, which told them something about the magnetic features of the material. They saw that the material remembered the magnetic field it had been in earlier when it was around 173 100 Kelvin. An effect on memory around 23 degrees Celsius to 250 degrees Kelvin. Another important observation was made that they think may have something to do with the temperature at which the material becomes superconductive, which means it conducts electricity without resistance. Patterns of magnetism were also seen. The researchers also watched how the magnetism changed when they increased and then decreased the strength of the magnetic field. They found that the material's response to the The magnetic field was different at higher temperatures than at lower temperatures. They saw some strange patterns in how the material responded to the magnetic field, which could be because of how the material is built on the inside. Remembering the last magnetic field it was exposed to for the first time, they noticed that when they applied a magnetic field for the first time, the material resisted the field even when it was only very weak, which wasn't normal at room temperature. They saw that the material's magnetic reaction changed when they changed the strength of the magnetic field, which points to a complicated magnetic response. They used a method called X-ray diffraction to look at the structure of the material and found that it mostly matched a known structure, with a few small differences that could have been caused by flaws in the material. Important overall conclusion: scientists found that the material has interesting magnetic properties, such as potential superconductivity, zero electrical resistance, up to 23 dkc. However, the effect they saw was very weak, so they need to do more work to make a material that shows these properties more clearly. Now let's look at some of the tweets that were made about this news. Professor of Inorganic and Materials, taking chemistry at UCL Robert Palgrave expresses doubts about the creation and description of a sulfur-desired material talked about in a study. Here is an outline of his main points. The synthesizing method is being questioned. Palgrave starts by looking at how the Sulu stomach is made. For the method, phosphate and lead sulfide are mixed together, but the exact makeup isn't known, especially when it comes to where the lead sulfide comes from. Copper issues with the conditions of chemistry. He says that the hydrothermal method, which is basically a high-pressure cooking process, is not usually used to make sulfoapatites. For example, heating the sulfide anion under pure oxygen at 500 deg Cs could easily turn it into sulfur dioxide, which is different from other known ways to make similar compounds. Analysis of methods for characterizing Palgrave says something about it. He uses powder X-ray diffraction to describe the material and notices that the XR pattern fits almost exactly with what he expected it to look like. However, he is worried about the lack of detail in the presentation and wants to know if background removal was done in the XR analysis. Not enough study of makeup. One important point he makes is that the study doesn't do any chemical analysis. He adds that while guesses be made about the presence of sulfur from the XRD data, stronger methods should have been used to prove it. Overall, there is a lot of doubt. In his conclusion, Palgrave says he isn't sure if the experts have successfully made the Solopcan. As was said, he agrees that the idea behind the study is interesting, but stresses that the method and proof are not good enough, especially when it comes to giving specific descriptions of the people involved. Verification of the material's composition. To sum up, Palgrave criticizes both the synthesis method and the study's lack of thorough definition, which makes him doubtful about the success of making the sulfo-taste material as described. Christian Kyle, the head of staff at Astronomy Space Technology, said that a researcher behind the new possible room temperature superconductor just did a new interview that talks about how they have only made a few hundred nanometers of the new material so far. They know that their data isn't enough to draw a final conclusion, so they're being careful and only calling it data that potentially indicates superconductivity. They thought they had ruled out ferromagnetism as a possible explanation for their findings. The results. The next step is to make their composition up to the millimeter scale or bigger so that they have more to test. Once they've done that, they'll keep testing with the other, more common superconductivity tests. 4-probe DC resistance measurement, moving sample magnetometer for mirror effect specific heat jumps, and other standard methods are used to check superconductivity. Scanning, tunneling, microscopy, and photoemission spectroscopy worked well for JOS. What's next for LK99? LK99 South Korean researchers will give a talk at the APP's March meeting 2024 on March 4, 2024.